Assalamu alaikum brothers. Today the experiment is about flip-flop and shift register. We know that flip-flop is the sequential logic circuit whose job is to store only a single bit, while the register is combination of flip-flops along with some control circuit in order to store more than one bit here. Okay, so in today's experiment we will explore different types of the flip-flop, which may be like the RS flip-flop. We will be doing an experiment about the D flip-flop and the JK flip-flop. And regarding the register, shift register, we are going to only do the shift right operation here. Okay, so I think you are already familiar with the flip-flops here. If you see here, in the flip-flop, I am just talking about the basic RS flip-flop here. In case of basic RS flip-flop, we have two versions here. One is the positive logic RS flip-flop, whereas the second one is the negative logic RS flip-flop. For both the flip-flop, we are given the truth table here. Okay, what we have here for the first one, for the negative logic RS flip-flop, we say that whenever the set input, S input, means S means set, R means reset. So whenever the set input here is 1 and my reset is 0, it will reset my flip-flop. Now I am using two terminologies here. One is reset and the other one is set. We say that when the output Q of a flip-flop is equal to 0, we will call it as the reset. And if the output Q of the flip-flop is equal to 1, we will say it's 1 here. It's a set state here. Okay, so for our SR flip-flop, whenever we have the set input 1 and reset is 0, it will reset my flip-flop, because we are talking about the negative logic RS flip-flop here. Similarly, we say that if my flip-flop is already in the reset state and we basically provide 1 1, means set and reset input equal to 1, there is no change in my current state, means it is reset, it will still remain reset. Now the other way, if for example I make R equal to 1, means I am saying that my reset R input here is 1 for the negative logic, what will happen? Basically it is going to set my flip-flop here. Okay, and whenever we give 1 1 here, it means it is going to stay as set, means there will be no change in my current state here. Okay, whenever we have 0 0 here, we say that I will get the Q and the Q complement same, which we call it as the undefined state. We also call it as the undetermined state, invalid state. You can also call it as the limbo state, LIMBO. Okay, the second one is about the SR flip-flop, but we are talking about the positive logic RS flip-flop here. Now in this case, this is the clock input, means the flip-flop will only operate if the clock input is equal to 1 here. Secondly, if I have 0 0 here, I am going to have no change state here. If R is equal to 1, it is going to reset the flip-flop. If S is equal to 1, it will set the flip-flop. In case of 1 1, it is going to be undefined state here. The next one is about the D flip-flop. We are going to do the experiment here. Again, whenever the clock here is 0, means my D flip-flop is not working, so it will remain with my current values, means there will be no change in my current state here. If my clock is active here, means 1 1, what will happen? If I give 0 here, my output is going to be 0, means the same reset state here. If it is 1 here, it will be 1, it means the flip-flop is in the set state here. Okay, the T flip-flop, we are not doing experiment, you can go through it. Okay, you should have studied in your theory section here basically. The next one is about the JK flip-flop. Now JK flip-flop has more or less the same inputs what we have for RS flip-flop. The only change here is basically instead of invalid state, we have a complement state here. Okay, so again in this truth table, as long as the clock here is 0, the output will be no change here. But when I give the clock equal to 1, it will run as the normal JK flip-flop output here. Like for example, if I give 0 0 here, there will be no change in my current state. Okay, if I give 0 1, means the value of K here is 1, so it will reset my flip-flop. If J is equal to 1, it will set the flip-flop. In case of 1 1, if you compare it with the RS flip-flop, it was basically a reset, it was basically an invalid state. But in this case, whenever we have 1 1 here, it will take the complement of your current state here. Okay, so this is what we are going to prove for our experiment here. So let's start the experiment here. You already have the experiment procedure with you, the procedure book with you. So just go through the procedure here. I have already made the connections here. Okay. For the first part of the experiment, we don't have to put these clips A3 and F4 and A4 and F5. So we don't have to use these clips here. Means these clips, I'm talking about these two clips. So we will run it without these clips here, okay? Because we need to close them in step 5 here. So now I have already connected the circuit here. So now let's suppose if I give the same, like I say that my A3 is equal to 1 and A4 is equal to 0. So you can see this one is your Q input, Q output. This will be the Q complement here. So basically the output here is 0. It means my flip-flop got reset here. So it means that this is basically your S input. Okay. Similarly, if I make it 1 1 during the same time, there will be no change in my current state here. Now we reverse it, means I make A4 equal to 1 and make A3 0. So it means the flip-flop becomes set here. So if I make it 1 1 again, so there is no change in the current state here. And if I make it 0 0 here, it is giving me an invalid state here. Okay, this is what we studied for the negative logic RS flip-flop. Similarly, okay, now what we are going to do, we are going to connect the second one. For the second one, basically we need to put these clips here. We need to put these clips and this one here. Okay, so let us put these clips here. Okay, this is the connection diagram now. We have already installed these two clips here and we made or completed this complete figure here. Okay. Now let's suppose if we try to fill this table here. First of all, if we give 1 0 here, for example, I say that A1 is 1, A1, this is my A1, this is my A1. So A1 is 1, A2 is, A5 is 0. So the output means my Q output is equal to 1 and this will be, the other one is, this one is 0 here. Okay. At the same time, keeping it, if I make it 0 0 here, what will happen? There is no change in my current state here. So basically, we are talking about the positive logic RS flip-flop. In the positive logic, 0 0 means there is no change in the current state here. Now, if we change it or reverse it, means I make A5 equal to 1 here. So my flip-flop got reset now. If I make it reset now, if I make it 0 here, if I make it 0 here, it means there is no change in the current state. If I make both of them 1 1 here, so this is an invalid state, means my Q and Q complement value is 1 at the same time, which is not allowed basically. Okay. Okay, let's do the experiment about the D flip-flop here. What was the D flip-flop? It means the data flip-flop here. Means as long as my clock is active, the output will be same as my input here. If the clock is 0, it means there will be no change here. Okay, you can say 0 0, maybe whatever. Okay, means there is no change in the current state here. So let's suppose here I have connected the same figure given to us in here. So you can see here basically this is the connection we have. So what we are saying here basically, whenever we clock 0 means we don't have to do anything here. Okay, we are using a pulse switch for the clock here. So if you change the value here by keeping the clock 0, there is no change in the output here. Okay. Secondly, for example, for the second one, if I make A1 equal to 0 and I give one clock pulse here, if I keep this one equal to 0 and I give one clock pulse here, it will reset my flip-flop here. If I make this one 1 and I give a clock pulse again, it will set the flip-flop. Okay, so this is your D flip-flop. Depending upon this value, if I give the clock pulse here, it will give me the value based on whatever I am giving on the switch here. Okay, now let's do the experiment about the JK flip-flop. I have made these connections which is available in the manual on the board here. Okay, just go through it slowly, you will find what I have done here. Okay, the simple connections here. Now let's suppose we try to fill the table here for a JK flip-flop. What we need to do here, first of all, we need to make the value of A1 and A5 equal to 0. So A1 and A5, I made them 0 and I give one clock pulse. So if I give one clock pulse, the value of X6 is 0. Okay, so you can write 0 here. It means this is a no change state here. Next one is I need to make A1 equal to 1. So this is your A1. I make it 1 here and I give one more clock pulse here. If I give one clock pulse, it means it become 1, so it means it has set my flip-flop here. Again, I will change the figures here and I change the connections here or switch, and I give one clock pulse here. It has reset my flip-flop. If I make it 1 1 and if I make it 0, so it means it has given me the complement state. Previous state was the reset and it will give me the set state here. Okay, so this is your JK flip-flop, and by using the value of the output, you can find whichever input here is J or K here. Okay, it's task for you, you need to find it yourself. Okay, the last one is about doing an experiment with a shift register here. Okay, what we have, if you see here, this is a shift register here. We have 4 flip-flops in this register here. So to operate it is simple. Okay, what we have to do, first of all, we need to first make the switch 0 equal to 0. When you make it 0, switch 0 equal to 0, what will happen? It will clear all the flip-flops here. Okay, so if I want to record something in this shift register, I need to make the value of switch 0 equal to 1. So I will make it 1 here, then I can store something. Next thing is in the A input here. In the A input here, this one, what I need to do here, I need to first give these inputs here. I will give 1 here and I will send one clock signal. One clock signal means using the pulse here. Clock signal means using the pulse from here. So what will happen here, when I give a clock signal using the pulse here, whatever I have, the input I have, it will be recorded in my flip-flop here. Next time, what we will do, if I again keep the same input which is equal to 1 and I give another clock here signal from the pulse switch, what will happen? The previous one will shift to the next register, means this one will come here and the new one will come here. Okay. Next time when I give 0, so 0 will come here, this one which is already here will be shifted here and this previous one will be shifted here. So after the 4 clock cycles, what will happen? I will get 1 1 1 1 here in my shift registers here. Okay. Now what we say, if we he says that observe the output display. Okay. What is the output display of the after 4 clock? Simple. The last value which I have here will be my output display after the 4 clock. So does it correspond with the input sequence? So this is your input sequence. This one is your input sequence, and obviously the value here will be starting from the down. It will be 1 0 1 1 here. Okay, so obviously it corresponds with your input sequence. Next thing is observe the output display of F4. Okay, if I only see F4 here, the last value here, he said does it correspond with your first input? Obviously this one here after the 4 clock cycle is basically your first input, which reach here after 4 pulses here. So basically it corresponds with your first input here. Next thing is, if I send another clock, okay, I can assume any input, like for example A equal to 0, and I give one more clock pulse here, like from here. When you give a clock pulse here, what will happen? This input will come here and all the previous input will be shifted here, and the last one means here, the previous one, it will go out here. Okay, so basically he said does it correspond with the second input? If I observe F4 again, this is basically my second input, which after 4 clock has reached here. My first input has gone out from the shift register here. Okay, so he said that we can call this one as the serial input, serial output, because basically we are only assuming one input and we are assuming one output here. Okay, so this was all about the experiment. I hope it will be clear for you.